Hello, and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. I'd really like to take a moment to thank all of you who listen to this show. I am constantly humbled by your interest and offers of support. Thanks to you, the show keeps reaching more and more people, with last week's show being our fastest ever to 5,000 listens in just over 24 hours. So please keep reaching out via the show notes page, Twitter, Facebook, YouTube, etc. We really love to hear from you. Inspired by listener Bethann NYC on Twitter, we want to try a little contest for you. We've got some fresh new stickers on hand, and we'd like to get them into your hands. I've got to say they really turned out great. So here's what you need to do to get one. Let us know your favorite quote from today's podcast via Facebook, Twitter, YouTube, or SoundCloud comment, or comment on the show notes page by midnight Sunday Pacific time, and we'll send you one. Before we jump into our show, I wanted to remind you to check out the Future of Data Summit that I'm organizing. It'll take place in Las Vegas in May at the Interop ITX conference, and I'm excited to have already heard from a bunch of TWiML listeners making arrangements to attend. We'll be covering some really exciting topics, including, of course, machine learning and AI, but also IoT and edge computing, augmented and virtual reality, blockchain, algorithmic IT operations, data security, and more. It's going to be a great event. You can learn more about the summit at twimlai.com/futureofdata. And now about today's show. This week, our guest is Stefano Ermon, Assistant Professor of Computer Science at Stanford University and Fellow at Stanford's Woods Institute for the Environment. Stefano and I met at the Rework Deep Learning Summit earlier this year, where he gave a presentation on machine learning for sustainability. We spoke about a range of topics, including incorporating domain knowledge into your machine learning models, dimensionality reduction, and his interest in applying machine learning and AI to addressing sustainability issues like poverty, food security, and the environment. And now, on to the show. Hello, everyone. Welcome to another episode of This Week in Machine Learning and AI. I am here with Stefano Ermon, who is an assistant professor at Stanford University. Stefano and I connected after his presentation at the recent Rework Deep Learning Summit, where he spoke on machine learning for sustainability. Stefano, why don't you say hi to the audience?
Hi, everybody. Thanks, Sam, for the invitation. It's great to be here with you today.
I'm really excited to have you on the show. I enjoyed your presentation and spent a little bit of time looking into some of the work that your group is doing at Stanford, and I found a really interesting mix of fundamental research into machine learning techniques, as well as a strong interest in a particular application area, notably sustainability. So why don't you get us started by talking about, how those two kind of meld for you and how you arrived at your area of focus?
Sure, yeah. So a lot of the research that we do in my group is really at the foundation, artificial intelligence and machine learning. So we do a lot of work on probabilistic modeling of data, developing scalable and accurate inference techniques for high-dimensional probabilistic models of data, knowledge representation, and decision-making under uncertainty techniques. So we're really interested in the whole pipeline of going from data to extracting knowledge, extracting insights from the data, to using these insights to improve the way we make decisions. And as a lot of the work is really foundational, so we prove theorems, develop algorithms, develop new models. But we also like to think about real-world problems. And I'm particularly excited about new applications areas for AI and machine learning. And as you mentioned, one that I'm really excited about is this new area of computational sustainability, where we're trying to apply computer science techniques and generally use ideas from computational thinking to help solve and address some of the big sustainability issues of our times. And these include things like poverty or environmental issues or energy, sustainable energy problems, natural resource management, problems in ecology, and so forth. So I'm very, very interested in finding ways to use these new amazing technologies that we've been developing in the past 10 or 20 years in AI and machine learning, and use them to address problems that are extremely important, I think, but perhaps they are not studied as much as they should in the field of machine learning and AI.
I think you're right that they're not studied as much as they should be. How did you arrive at that research focus as opposed to one of the more popular or buzzworthy areas like robotics and or even here in the Valley, getting people to click on ads?
Right. So it all started with my PhD, actually. So I did my PhD in computer science at Cornell University. And right when I joined, my advisor had just received a big grant from NSF, an expedition in computing, to start a whole new research area in computer science. And the idea was really to try to see whether we can take all these amazing techniques and ideas that we have and use them to address problems in the public space. The idea being that information technology and computers and AI have really revolutionized the way people live and a lot of way people do businesses, and they really changed the world. Mm-hmm. But if you think, on the other hand, at the way we try to solve some of the big societal problems that we have in the public space, dealing with the environment and how we manage our natural resources, or how we try to sort of close the gap between developing and developed countries, we're still not taking advantage of all these ideas, just because there's not so much economic incentive to develop the necessary models, develop the necessary algorithms, figure out how to actually use them to solve these problems. And so, that was kind of how it got started, and I've been working on those kind of problems basically ever since. So for almost 10 years now.
Very nice. Now, in your presentation, you shared some statistics around the impact of the problems that you're going after with regard to poverty and food security and the environment. In many ways, I think it's kind of obvious that these are important issues, but like you say, in a lot of ways, they're understudied because of the lack of a driving economic incentive. Can you share some of those stats, or at least the ones that inspire you to continue pursuing this work?
Right. Like, I was actually looking at the 2030 Agenda for Sustainable Development that was recently adopted by the United Nations. And if you look at the kind of problems that were sort of identified as being some of the big societal challenges that all the governments in the world should be working together to address, we see things like ending extreme poverty. There are still hundreds of millions of people around the world living in extreme poverty, or eliminating hunger. It turns out that, again, there are lots of people, especially in places like Africa and Asia and so forth, that don't have enough to eat. Or, protecting biodiversity. There's this huge biodiversity loss, and we need to find ways to manage our resources in a more sustainable way so that we can sort of guarantee the welfare not just of our current generation, but also our children and the generations that will come after them. So these are all big, important problems, and a lot of them, one of the challenges why they are so difficult is partially because they involve this sort of global scale phenomena, like thinking about, say, climate change, or how to manage these very large ecosystems, or the fact that we need to deal with multiple agents that have different objective functions and they're interacting with each other. But there is clearly like a computational component to these problems, but so far it has not been studied so much. And so one of the focus of my research is really to try to find ways to apply these techniques from AI and computer science to help address some of these issues.
And on that note, Do you come at things from the perspective of, as you said, applying techniques that are developed in AI and machine learning research to this application area, or the other way around, meaning identifying specific problems in the research area and using those to drive research around specific techniques?
That's a great question. I actually like to think of it as a two-way street, where from
so
the
yes and yes.
Yes. On the one hand, sometimes we start with a problem and we realize that maybe we don't have the tools right now, or we don't have the right models to address that problem. And that often happens because this problem have not been studied so much in computer science. So there's always some aspect of these problems that has not been studied before, or some variation that sort of gives rise to a new problem, and that will require new models, new algorithms, and we can sort of publish our papers in sort of top AI and machine learning conferences. And on the other hand, we also like to do a lot of foundational research, and so sometimes we know about all the capabilities sort of that we have right now at the cutting edge of AI and machine learning. So just by talking with my colleagues at Stanford, sometimes I hear about, I ask them what are the problems that they are working on, and we try to find ways to use these new ideas and apply them to help them solve these very important problems.
So one reason why it's interesting that you take this two-way street approach is because I spend quite a bit of time following companies that are trying to democratize machine learning and AI. And often what they're doing is trying to create generalized machine learning and AI platforms. And, in fact, all of the large cloud companies like Google, Microsoft, and Amazon are trying to do that same thing. But then we have a group like yours that, has a fundamental focus on a specific application area that drives, deep, unique research into the field. I'm wondering what's your take on that? Do you feel like what's your take on the role of kind of generalized machine learning and AI techniques and versus very application specific techniques? I
think there's definitely a lot of value, like in sort of developing tools and frameworks that can be easily used by people that might not necessarily be domain experts. I think, and that will definitely help in a lot of contexts, including in the sustainability space. But I do believe that sometimes you really need to develop. There is some actual research to be done. There are some problems that require actually new techniques. And so there's definitely a lot of space for developing new ideas, new models that maybe are motivated by this specific application, but then they can be potentially applied down the line to other problems that in completely different domains. I mean, that's kind of the beauty of computer science, is this idea of abstraction, that we develop these general models, these general algorithms that are maybe inspired by one specific problem, but then a few years later somebody else comes up with a completely different and new application that you would never have thought about, and they apply exactly the same algorithm to this new problem.
Right.
I think that's really the power of computer science, these layers of abstraction.
Right. So let's maybe try to get more concrete and talk through some of the specific research that your group is doing and how it's uniquely applied in this application area. And one of the papers that I came across on your group's website, which I'll link to in the show notes, is one on deep Gaussian process for crop yield prediction based on remote sensing data.
Yeah.
Crop yield prediction is, we'll talk about the importance of that problem and the data source, and then walk us through kind of what the research is hoping to achieve.
Yeah, so that particular paper, we were looking at problems in the food security space. It turns out that there are, as I mentioned earlier, there are lots of people around the world that don't have enough to eat, and suffering from various kind of food crises due to weather, climate change, land like erosion, or like rising waters. All sort of problems are kind of causing these food security issues. And we know that the situation is going to get worse with time. The world population is growing, and we're going to have to find a way to, there's an estimated, I think, 2 billion more people that we're going to have in 2050, and we're going to have to find ways to feed this growing population. And so the kind of problem that we looked at was that of trying to see whether we can use inexpensive, cheap, unconventional data sources like satellite data to keep track and predict various food security measures and monitor agricultural outcomes. So in particular, we try to develop these machine learning techniques to predict, just by looking at the images of the Earth from space, to predict how the kind of level of agricultural productivity of a geographical area just by looking at it from space. So essentially, we developed some machine learning models that can track the growth of plants from space and use that information to predict ahead of time how much in that particular application we're looking at soybeans, but since then we've extended it to corn and other crops. We are able to actually predict very accurately from space using cheap unconventional data sources the level of productivity of different geographical regions. And this is important because given this kind of data, we can start collecting this kind of data, especially in developing countries. It's very expensive. We don't have much data on this kind of measures in places like Africa. And so if we had a way to measure this, say, crop yields or other food security measures like stunting or things like that, that could be extremely useful to improve the kind of policies that both governments and NGO use, things like predicting whether there's going to be a famine in a certain region or whether a certain government should stock more, increase the levels of sort of food reserves in case that there's an emergency and things like that.
And so in this particular case, remote sensing data, the satellite imagery, where did that come from? Is this Google Maps type data, for example, or Google Earth type data, or a government or proprietary data source? It's
actually publicly available data. We were using data from NASA, the MODIS satellites. So this is publicly available data. They take an image of basically the entire world every 8 days. And this is multispectral data. So it's not just sort of like visible RGB bands, but there's also infrared and other bands that contain additional information that we can use in our machine learning system to make our predictions.
Okay. So you started with the goal of taking this multimodal image data and trying to predict crop yields based on it. And along the way, developed some new techniques around one that was called out in the paper is dimensionality reduction. Can we spend some time talking about that particular technique and its novelty, and even the step before that, for folks that aren't familiar with it? What is dimensionality reduction and why is it important in this problem space?
Yeah, so the challenge in this for this kind of application is that we didn't have a whole lot of training data available. Like these days, if you have a lot of training data, then you can take a sufficiently high capacity model, like a big, large neural network, say, and there is a high chance that with a sufficiently large amount of training data, you will be able to do a pretty good job at predicting these kind of outcomes that we care about. But in a lot of the sustainability applications, like in this case for predicting crop yields, and also we did some other work on predicting other kind of socioeconomic measures of interest like poverty. It turns out that the amount of training data available is extremely limited. It's very, very scarce. And so you cannot just train a machine learning system, a state-of-the-art machine learning system end-to-end from inputs to outputs. And so what we did is we've been developing several techniques to try to get away with less training data. One in particular that we use, the particular dimension, which And there are several ways to do it. Sometimes, and essentially in all the cases, we either do transfer learning. So we try to use some proxy for the measures that we care about to get some signal and maybe pre-train the system and learn something useful about the structure of this kind of multispectral images that we use as input. Or we use some kind of prior knowledge, maybe something about something that we know about the outcomes that we're trying to predict, or relationships between input and outputs, and we can use it. We can sort of put that into the system to make sure that we can basically get very good results, even when we don't have a whole lot of training data. In this particular context, the dimensionality reduction technique that we used was an idea that we had to essentially reduce the dimensionality of the inputs. An image is very high dimensional. You have a lot of pixels and they can take many different values. So it's a very high, sort of the input data lies in a very high dimensional space, although there is a lot of structure. And so in some sense, the information that we care about is actually can be extracted from without really looking at the exact position of all the pixels in the image. So what we came up with was an idea to reduce the dimensionality of the inputs while preserving most of the information content. And the idea was fairly simple. The idea was that, well, if you care about predicting crop yields, it doesn't really matter where the fields are in the image. So the soybean fields are in the image. Their actual location doesn't matter.
You said the what fields?
Let's say the soybean fields.
Soybean fields, okay.
The actual position in the image, whether they appear in the sort of top right corner or the left bottom corner, doesn't really matter, right? So you can use this prior knowledge to essentially reduce the dimensionality of the inputs while preserving the information content. And that makes learning the problem easier.
So when I think about the image problem, in what way is that a high dimensionality problem? And, how do those dimensions correspond to the actual problem space?
Well, you have basically one dimension for every pixel in the image. So if you have, like 1,000 by 1,000 pixels, there you have like 1,000,000 dimensions for your inputs. And that's essentially what's causing the problem. It's very high dimensional, and so it's known that a lot of machine learning algorithms, a lot of algorithms in computer science, they suffer from this curse of dimensionality problem. That as the dimensionality grows, the volume of objects grows exponentially fast. And so kind of the coverage that you have of this very high dimensional space by getting samples that you have from your training data is extremely, extremely sparse, which is so high dimensional, and you have like so few points that makes it very different to sort of infer something about what is going on in this very high dimensional space. And so you have to use some kind of prior knowledge to realize that actually, there are certain things that don't really matter. We are looking for things that maybe are translational, invariant, or maybe, we know that some bands don't matter, or we have some kind of inductive bias on that we can use to and put that knowledge into the system so that we can still do something useful, even though the inputs are so high dimensional.
So in this case, dimensionality reduction, another way of thinking about that is just getting your machine learning algorithm to focus on the important parts of the thing that you're trying to train it on, as opposed to the entire space of the images.
Exactly, yes.
And so you mentioned another thing you mentioned in terms of techniques for accomplishing this is transfer learning, which is applying pre-existing models as kind of starter models to training application-specific models. Is that the way you would describe that?
Yeah. So the idea is that you typically have a task in the case of machine learning that you want to solve, and maybe you have a limited amount of training data for that task. And so you can set up a different but related machine learning task for which you have plenty of training data available. And by trying to learn how to solve this new task, the hope is that you are going to learn something useful. You're going to learn some skills that then you can transfer to your original machine learning problem that you care about.
And this is often done with models trained on like ImageNet data, for example. Is that something that you guys did in particular, or did you apply other models to this particular problem? And how did you go about thinking about where to start?
Yeah, so that's ImageNet is often a great place to start with if you're looking with if you're dealing with sort of natural images. One challenge in our application domain is that we were looking at satellite images, which look very, very different from the kind of images that you can find in ImageNet. They are not object-centric, like there's not a single object in the middle, like you typically have in ImageNet. They are taken sort of like from this bird's eye perspective, which is very different from ImageNet. They have more bands, so it's not just RGB, but you have a whole set of other bands that you don't typically have in ImageNet. And so the kind of typical features that a network, say a convolutional neural network pre-trained on ImageNet, is able to discover do not work well when dealing with satellite images. And so what we did was to come up with other transfer learning ideas. This was actually for a slightly different problem in which we were trying to predict the distribution of wealth and poverty, in this case, in developing countries. Again, we were trying to do this using cheap, unconventional data sources. In this case, we were using high-resolution satellite images. While there is very little data on poverty, there are many African countries that have not taken a nationally representative survey, maybe in a decade or so. Satellite images are available in basically every part of the world. They get updated very frequently. And they contain a lot of information about various types of socioeconomic outcomes, both in terms of poverty, wealth, but also agricultural outcomes, like we were just talking about before in the context of crop yield prediction. And so the problem that we were looking at in that paper was that of trying to predict various types of poverty estimates, like asset-based measures of wealth or other measures of poverty based on income, again, using raw satellite images, which are widely available. And the challenge was that, again, we have very limited training data available to train these models. And so we had to do some transfer learning. And there, the idea was that it turns out that there are satellites that take images of the Earth both during day and during night. And so during night, you get to see sort of the amount of nighttime light intensity associated with essentially every region in the world. And it turns out that nighttime light intensity is heavily correlated with the level of economic activity. Like if you haven't seen it, you should try to see the difference between, say, North Korea and South Korea. You're going to see that South Korea almost looks like an island at night because North Korea is so dark at night. And so the idea there was to see whether we can train a machine learning model to predict the amount of nighttime light intensity for many locations across the world just by looking at the corresponding daytime images. And we could do that. And this is a task for which we have essentially an infinite amount of training data, because these satellites are continuously taking images both during day and during night. And the hope was that by training the model to solve this task, it would discover features that are somehow related to the level of economic activity. And it turns out that it is indeed the case. It turns out that if you train a convolutional neural net to solve this task, and then you sort of try to visualize the features that the network learns, you discover features that are very semantically meaningful. Like there is a filter that learns how to recognize roads. Other filters try to identify different types of houses or other features of the landscape, like farmland, whether there are roads with lots of traffic or not, even swimming pools. And the nice thing was that this was all discovered in an unsupervised way. Like we never told the network, look for houses or provide labels of what a road is or what a house is or what a swimming pool is. It really discovered these semantically meaningful features by itself, purely by solving this transfer learning task of trying to predict nighttime light intensity from daytime images. And then what we did was to use these features that we learned in this transfer learning task to actually predict the various poverty measures that we cared about. And because we had such good features, again, we were able to get very high accuracy, even though we had a very limited amount of training data corresponding to these poverty metrics that we cared about predicting.
Wow, very, very interesting. What do you recall the name of the paper where you describe the transfer learning technique?
So we had 2 papers on this. There was a paper, a AAAI, which is called Transfer Learning from Deep Features for Remote Sensing and Poverty Mapping. Mm-hmm. And then we had a follow-up paper on Science called Combining Satellite Imagery and Machine Learning to Predict Poverty, where we actually detailed the kind of results that we got in predicting poverty across 5 African countries. And we showed that it can really outperform all the previously existing techniques by a large margin.
So in that, what were, without totally losing our place on the crop yield prediction, maybe can you talk through some of the techniques that went into the transfer learning work?
So that's essentially the key, sort of the gist of the idea of the transfer learning, trying to find a task that is somehow correlated with the one you care about, but for which you have a lot of training data. We didn't actually use transfer learning for the crop yield prediction. We just used the dimensionality reduction. The other thing we used was an idea called semi-supervised learning, which is another approach that you can use when you have a small amount of labeled training data and a potentially very large amount of unlabeled training data, which is, for example, the case in our applications where we have a lot of satellite images, but we have a very small amount of labels corresponding to sort of the amount of soybeans that were produced in different regions, or the poverty, sort of like survey-based measures of poverty in developing countries. And the kind of technique that we used to do semi-supervised learning in this case is a combination of neural networks with Gaussian processes. The idea is that we're trying to predict things that have a lot of structure. Like we're trying to predict the distribution of, say, wealth or crop yields across space and time. And we are expecting these outputs that we're trying to predict to change slowly as a function of time and space. Mm-hmm. And so that's some kind of prior knowledge that you can incorporate into the model. And we did this using a Gaussian process, which is a probabilistic model that you can use to model all sort of things, but it's very popular in the geostatistics community to sort of model functions that over space and time. And you can use this probabilistic model to not only make predictions, but also to measure the uncertainty that you have when you make predictions at new locations for which you don't have training data.
And so is the Gaussian process primarily used spatially, as you just mentioned, or is it also used in time, meaning I've got a label at some point in time, but I don't know how the value of that label changes over time, so we apply a Gaussian to that, or both of the above?
Both of the above, yeah, in our case. We were looking both over space and time. Okay. So in general, you can use Gaussian processes over any kind of input space. They're often used to model functions that change sort of over space and time. And the key thing that we did was to combine this with neural networks. For each location in space and time, we have a corresponding image that is collected by a satellite. And so we somehow want to include that information to inform the predictions that are made by this Gaussian process. Mm-hmm. And the idea was that we could somehow extract features from an image using a convolutional neural network, and then use these features to gather sort of the spatial and temporal structure of the problem to make predictions. And the nice thing about the Gaussian process is that it not only allows you to make predictions, but again, it lets you quantify the uncertainty that you have when you make predictions and new unlabeled data points. And so our idea of doing semi-supervised learning was to sort of jointly train the neural network and the Gaussian process in order to achieve a good fit at the points for which we had actual labels, while at the same time trying to minimize the uncertainty at points for which we don't have labels, points for which we have the inputs, but we don't have the outputs. And it turns out that even though we don't have the actual sort of output for these unlabeled data points, the Gaussian process will still be able to make a prediction and will still be able to quantify the uncertainty of this prediction. So we can jointly train both of them to actually minimize this measure of uncertainty. And that's essentially how we use the unlabeled data points together with the labeled ones to in this semi-supervised learning framework. And in some sense, it's a form of regularization that is sort of forcing the model to look for features that are not only useful for the labeled data points, but they are also relevant for the unlabeled data points. And it turns out that by using this framework, this semi-supervised framework we developed, we were able to further improve the accuracy in both the poverty prediction tasks and the crop yield prediction task.
Okay, so taking a step back, you've got this image data from the satellites that is, has pixels, but is multimodal, so it has multiple pixels for each location. When you talk about making a prediction from a particular point, what's the granularity there? Are you predicting the level of wealth or poverty from a pixel, or are you somehow aggregating multiple pixels to form an area?
Yeah, good question. So we were making predictions at the 1 kilometer by 1 kilometer sort of areas, which correspond to multiple pixels. So for each sort of location, we would collect multiple images that would cover that location, and then we would sort of aggregate all the information and make a prediction for that area.
Okay. And so you've got all this input data. You're feeding that input data into a convolutional neural net, which is essentially taking kind of various chunks of the images and translating them, rotating them, things like that, to try to identify what are the salient features within the images.
Yep.
And then I guess the question that I'm getting at is how and, where do you marry the Gaussian stuff with the CNN stuff? Is that a training? Is that a step that's taken in the training? Is that a feature of the model architecture? How do they tie together?
Yeah, you can think of it as both. So you can sort of think that there is one neural network making prediction at each different location, but then all the predictions that are made across different locations are all tied together because we know that the outputs are spatially correlated. So if you take two locations that are close to each other, we know that we sort of expect the outcomes that we're trying to predict to be more similar if the locations are close to each other. And we know that empirically, if you plot a variogram that is measuring this, there is a lot of spatial correlation in this kind of things that we're trying to predict. And so you can imagine the Gaussian process as an extra layer in your neural network at the very end that is kind of coupling together all the outputs of these of the predictions made by all these various convolutional neural networks. And by using this, you can sort of exploit this prior knowledge that you have about the spatial and potentially temporal dependencies across the outputs.
How many layers did the network end up having? Do you recall?
We experimented with several architectures. I think the one in the science paper, it was based on a VGG network. More recently, we've been playing with ResNet, so 50 layers, and those tend to work even better.
And do you have a sense for the relative performance, with and without the Gaussian layer? Or I imagine that's what you talked about in your paper. But was that, fundamentally, did the Gaussian layer make this possible, or was it adding an incremental boost in performance?
It's adding an incremental boost in performance. I think you could have gotten some reasonable results even without the Gaussian process, but the Gaussian process definitely helped by maybe improving by maybe 10% or 15%, something like that.
Was there anything in particular else that you learned about the process of architecting networks for this type of problem in the context of this work? Well,
one thing, the thing that matters the most is that somehow there is it's quite interesting how we started trying to sort of inspire the architectures and try out networks that were sort of loosely inspired by what our domain experts would tell us was important. Say in the context of crop yield prediction, there has been quite a bit of work in the remote sensing literature in coming up with handcrafted features and various types of indexes, combination of various bands that they think are going to be predictive of vegetation growth and therefore also crop yields. And it turns out that if you actually train the neural network to sort of discover the features by itself, just by sort of doing representation learning using a modern machine learning approach where we let the data speak for itself and sort of try to identify which features are relevant directly from data, it turns out that our model ended up using very, very different kind of sort of different inputs ended up mattering much more for our model than what was previously thought in the remote sensing literature. So some bands that people thought were not particularly important for crop yield prediction ended up being very, very important for our neural network and vice versa. So I think it's similar to what happened in computer vision, where people for a long time were handcrafting features. And then it turns out that if you sort of train end-to-end the neural network, you can do a lot better than anything sort of people had all the kind of handcrafted features that people had come up with over the years. And so something similar was happening also in this case, that using this modern machine learning techniques, we were able to come up with very different features than what was previously thought was used.
And do you attribute the difference between what your models came up with and what domain experts tended to use with biases on the part of the domain experts, with confounding factors in the model or the use case? Any particular insights there?
So unfortunately, these neural networks are very powerful at making predictions, but it can be hard to really, they're not very interpretable. So right, it can be very hard to figure out exactly what they're doing.
We talk about that problem quite a bit on the show. So.
Right. So we had the same issues and sort of trying to understand and trying to explain what this model is doing was very hard. And so we don't have a good sense of why at the moment. It's something we're actually actively researching, and we're really trying to understand what is this model capturing and why does it perform so much better than previous techniques. But I think we're going to need probably entirely new techniques to figure out these issues in a more principled way.
Mm-hmm. When you describe the approach of using the nighttime imagery to train the model on the daytime imagery, it reminded me a little bit of another one of your recent papers, also a AAA paper from this year on the label-free supervision of neural networks with physics. And so there are a lot of parallels there, but this one, the context in which it's talked about in this paper is kind of an interesting one, where you've got models that you're trying to predict. Well, I guess I should allow you to explain. Why don't you go ahead and explain what the focus of that paper was?
Sure. So, I mean, it fits into one of the general themes that I'm very excited about, which is this idea of trying to incorporate domain knowledge into machine learning systems.
Yes.
So find ways to provide supervision that are alternative to coming up with millions of labeled examples. And so the idea of doing semi-supervised learning, the idea of doing transfer learning, the idea of sort of doing the various dimensionality reduction techniques fits into this broader agenda of sort of like trying to see whether we can go beyond this labeling, which is really a major bottleneck and is really preventing us from applying these machine learning techniques in domains like the kind of applications we are interested in the sustainability space, where the labels are just not available. And even if you wanted more labels, you could not get them. Right. Like we a couple of months ago, I sent we were running our model in Somalia. We were making poverty predictions in Somalia for the World Bank. And that's a country where they were telling me how they cannot even send their people on the ground to collect data because it's just too dangerous. And so we are really looking at problems where getting labels is not possible or it's just too expensive. And so we need to think about different ways to put in to incorporate domain knowledge into machine learning systems. And this particular AAA paper that you mentioned, we were looking at whether we can use prior domain knowledge, like knowledge about the laws of physics, to supervise object detectors in that case. So supervise convolutional neural networks and teach them how to recognize objects by providing sort of this high-level description of the kind of things the network should be looking for. So even though we don't have a precise label of saying, okay, here's the object that you should be looking for, one thing that we tried was to see whether it's possible to learn how to recognize these objects by providing a high-level description, like something like a loose description of the dynamics of the kinematics of the object. And we showed in that paper that it's possible in some cases. We provide some proof of concept demonstration that it's possible, for example, to train a convolutional neural network to recognize objects moving, falling sort of through the air, just by providing some prior knowledge about gravity, essentially, just by saying, well, I know that if an object is falling it's moving through the air, then there is gravity, and so the trajectory will form a parabola. Just by using this prior knowledge, it turns out it was sufficient to learn how to recognize objects moving in a video.
And so to be a little bit more concrete, in this paper, you used the example of projectile, in particular a pillow.
Yeah.
And from some of the images that you had in the paper, you can imagine a neural network getting confused between the pillow and the fluorescent lighting. And presumably the knowledge that you're giving it about the laws of motion, if you will, the physics of a projectile pillow, will help the network figure out where the pillow is.
Exactly.
And then it strikes me that perhaps this is relatable to your research on crop yields. And, for example, you may have knowledge about seasonality in the way, or if not crop yields, the poverty piece, but you may have information about seasonality and how tree leaf colors change over time, or there's all kinds of things that we know about the physical world. And one would presume that the more we can incorporate that into our models, the smarter those models will be.
Right.
And so how exactly do you incorporate that into a model? Is it an algebraic representation of some sort, or?
So in the TWiML paper, we were only looking at sort of like algebraic representation in the case of physics law, or using logical representation. We also had another example where we showed that if you know you have some prior knowledge that you can describe using logical forms, something like whenever object A appears in an image, then object B is also present in an image. Think this kind of relationship that can be fairly naturally captured using logic. It turns out it's a fairly natural framework for humans to model and to write down sort of prior knowledge about a particular domain. Those are the two things that we explored in the TWiML paper. We are doing some work right now on using simulators. That's another fairly common way in which we can formulate prior knowledge about the domain, especially in the physical sciences. We might have a rough simulator that gives us a sense of how a particular physical system behaves. And the question was whether some of the things we're exploring right now is to see how to incorporate say a simulator and put it together with data, unlabeled data, and see whether we can combine these things together and use the knowledge that is sort of inherently present in the simulator to provide supervision to say neural networks.
Mm-hmm. Yeah, one of the areas spending some time researching of late is industrial AI and how AI factors into control and optimization scenarios and, robotics and manufacturing and things like that. And the use of simulators is of key importance in those areas. So it's interesting to see you applying that here as well. So are we at the point where you have how generalizable is an architecture that can incorporate these types of rules? Meaning, is there, is a particular law of physics, baked deeply into the model architecture or the training process, or, can you envision some kind of architecture or a training regime that you can feed a, somewhat generic kind of rule or law engine that can bake this stuff in?
Yeah, that's a great question. So at the moment, it's all very much specific to particular constraints and particular forms of domain knowledge. At the moment, basically, you have to invest a considerable effort in sort of engineering the right objective function and figuring out how to bake in the prior knowledge into the system. So it's a different kind of trade-off where you're still spending a significant amount of time sort of providing supervision to the system, but the advantage is that it does not scale linearly in the number of in the size of your training data, right? Mm-hmm. So it's an interesting trade-off that might be advantageous in some situations. But the dream would be, as you said, to sort of come up with a general language that we can use or a general system that will make it easy to incorporate prior knowledge into machine learning systems. But we are not there at the moment. We don't have it, but I think that that's what we need in order to make sure that people can use these systems and they can really dramatically reduce the amount of training data that they need to solve their tasks. Maybe we're not going to be able to get away with the training data completely, like we showed in the TWiML paper, where we didn't use any label at all. Right. But maybe the hope is that it will work like for us, for humans, where maybe a handful of examples is enough to learn how to solve an interesting task, and maybe just a high level description plus a few examples is enough to solve the problem, as opposed to millions of labels, which is not how we learn, I think.
Right. So any thoughts on where you see this all going, or how you see it evolving over time, or even simply what you're most excited about right now?
Yeah, that's definitely something I'm interested in, trying to understand how to put in prior knowledge, how to combine it with labels in the most effective way. Also how to do unsupervised learning. That's another thing we are playing with these days. How do you discover structure from data, and how far we can push this thing, and really how much can we reduce the need for training data. These are all problems that I'm very excited about, and in thinking about what's the right way to represent knowledge and what's the right way to put the knowledge into the machine learning systems, and finally how to reverse the process. Like here we showed how we can put in some physics and we can make the machine learning system better, but ideally I would like to then invert this and try to distill physics and try to distill knowledge from the raw data. I want my machine learning system to come up with new hypotheses. I want it to discover gravity just by looking at the videos. And I think that's what's really, really exciting. I think we're still far, but I think that would be pretty amazing, because then we can really think about using machine learning also in the physical sciences. That's a space in which we haven't seen as much as not as much as in sort of other kind of application domains, I think. And so but there is a lot of potential for using AI and machine learning in the physical sciences, because they're doing more and more of high throughput experiments, collecting massive amounts of data, and sort of human time. Humans are really the bottleneck, trying to analyze this data, try to figure out what is going on, figure out trends, understand what is interesting, what is not. And if we had a way to put in machine learning and AI systems to help and sort of make the process easier, try to automate it a little bit or as much as possible, I think the benefits could be really huge.
Yeah, absolutely. So we talked about a bunch of your work, in particular, several papers. If someone wanted to, if it's possible to do this, kind of get up to speed on your research and the kinds of things we've discussed, are there, 1, 2, or 3 papers that would be the kind of key things to, help them understand what you're up to?
Yeah. So if you want to learn about the physics and the domain knowledge, there's the TWiML paper called Supervising Neural Network with Physics and Other Domain Knowledge for the sustainability applications. So there are the papers you mentioned, there's the science paper, and then there is the deep Gaussian process for crop yield prediction, which is also TWiML, discussing how to use the Gaussian processes and dimensionality reductions to deal with remote sensing data.
So those are the right places to start.
Yeah.
And just to close out, if someone wants to kind of learn more or get in touch or kind of follow you on social media, if you're out there, any particular coordinates you would point folks to?
Yeah, come to my website. It's just to Google my name. It's probably the first thing that comes up on Google. It's you can see all my papers or visit my research group website. Then you can see all the latest stuff.
Great. Well, we'll link directly to it in the show notes, so folks won't need to Google it. But this was a great conversation. I really enjoyed talking to you about the work, and I'm super excited about the work you're doing. The papers are really interesting, and I learned a ton. Thanks so much, Stefano.
Thanks for having me. It was a lot of fun too.
Bye-bye.
Bye-bye.
All right, everyone, that's our show for today. Once again, thanks so much for listening and for your continued support. Don't forget to share your favorite quote from this show to get one of our new stickers. You can share them via the show notes page, via Twitter, via our Facebook page, or via a comment on YouTube or SoundCloud. Please use the hashtag TWiMLAI on Twitter. The notes for this show will be up on twimlai.com/talk/15, where you'll find links to Stefano and the various resources mentioned in the show. Thanks so much for listening, and catch you next time.